Good morning, everyone. Can you hear me clearly? Do you hear me? Okay, I think you can hear me. Please respond.
Yes, sir.
Okay, good. Before starting the lecture, I think I got a message, email from one of you requesting some discussion regarding what? I mean, this course or which part you want? What kind of a discussion you would like to have? Or whether do you have any doubts or what to clear? So the message is, dear sir, requesting a discussion class for the subject of GL 211 due to the current situation of the country. We have to stay and do our academic works at home, and therefore we have to face some issues related to the academic work. Therefore, this is a kind request to arrange an online discussion class for the subject of descriptive mineralogy, and it would be great support for all of the students of the batch. Thank you. Yeah, regarding that, what can I do? What do you want from me? Can you just elaborate? If you have any issues, we can just quickly discuss, and otherwise we can have a separate time for that. Please let me know. Yeah, I mean, what do you want to have as a discussion class? Because we will do physically of these aspects as well when the university allows you to come into maybe in the late November. Most probably your batch will be asked to come according to the university sources, but still not sure what their final decision is. So can you just send me a message regarding what parts you need further discussion? Okay, we can have a revision. We can have a revision or whatever the discussion. I think first we will finish the content, and then we will have a discussion. Is that fine? I need only actually 2 classes is enough. But today I have to stop early because there is a meeting to attend. So anyway, maybe another 3 hours time I can finish the content related to the descriptive part. The other optical mineralogy part is being done by Dr. Dharma Priya, and the demonstrators are also doing some demonstrations, I guess, right? We arranged them. They started already. Did you attend those?
Yes, sir.
Okay, so it's very important that you attend those also. So are you happy like that? we will finish the content and then have a discussion, so that you can get prepared with the questions and what the doubts and all. Okay, so we will do like that. So I will continue with the continuation of the content, but you can send me an email or message specifically mentioning what kind of a requirement you have, right? Okay, is the screen clear to you? I just shared.
Yes, sir.
Okay. So we discussed about the pyroxenes or the inosilicates, single chain silicates. I think we stopped somewhere there. Okay. So just to revise what we did under pyroxene. So we can represent the pyroxene composition in a triangle, right? That is a very simple interpretation. There we take what? We take this one, magnesium end and iron end. Okay, magnesium end and iron end means the enstatite component and ferrosilite component. So this end member, magnesium end member of pyroxene is called enstatite. Iron end member is called ferrosilite. Okay. And then we have calcium end member also, but I mentioned that there is no specific real composition or the natural occurrence of a pyroxene in calcium end as the calcium end member, but there is one group of minerals forming with this composition, with this chemical composition. We will discuss it a little later. Okay, but I am not putting that as a real pyroxene there, right? Calcium end member, naturally existing calcium 100% calcium end member is not there. Okay, but when the calcium content of the pyroxene is increased here along this line, since this is a triangle, you have magnesium side and iron side, but along this side there is no calcium, right? So in the calcium is 0 along this side. So gradually, if you increase the calcium content, so you can get increased its composition like this, right? From 0 to some percentage, like nearly 50, right? Around here it's 50 calcium percentage. Okay, this side also 50 calcium, right? That means along this line it is represented 50 calcium, 50% of calcium component. Okay, so the clinopyroxenes, there are two types of pyroxenes according to this chemistry. One set is called orthopyroxene, right? So this orthopyroxene is the one that you have a calcium very limited amount, right? So you can see very limited amount of calcium is there, because you see orthopyroxene is limited to this area. Okay, it's limited to this area. That means around 5% like on maximum. Right here, if you see here, it's about 5% of calcium component. All the other content is composed of magnesium and iron, right? So orthopyroxenes are having very low amount of calcium amount component, almost 0 some cases, right? When the calcium content increases, actually the orthopyroxenes cannot exist. So they are no longer orthopyroxene, they are clinopyroxene. And also the symmetry is also changing, the crystallization or the crystal structure. Orthopyroxenes are orthorhombic. Okay, orthopyroxenes are orthorhombic and clinopyroxenes are monoclinic. So when it goes to the monoclinic system, calcium starts to accommodate into the structure. So in the monoclinic structure pyroxene only calcium can be accumulated. So that's why you have calcium in clinopyroxene. To form clinopyroxene, it is essential that you have calcium. Otherwise, clinopyroxene is not formed, right? So, but still, in this range, in this area, right? Calcium maybe from 10 to like 40, right? Calcium from 10 to 40 like range in this area. There are no naturally occurring clinopyroxenes. There are no such pyroxenes found in the planet Earth or any other planet so far discovered. Right. So there we term that region as immiscible region. That means solid immiscibility is there according to this chemical behavior of pyroxenes, right? So there is no mixing. That means in the solid solution, calcium cannot be mixed into the pyroxene structure in this region. That's the reason. That is the immiscibility region of pyroxene, right? No clinopyroxenes are there. But when it comes to a little bit higher compositions, that means if the calcium is little enriched in the environment where these minerals are crystallizing, it depends on the protolith also. Protolith means the parent material which can account for the rocks generation, different rock types generation. That means rocks means, you know, collection of minerals. For the protolith means the parental material of the rock. So that obviously indicates about the parental material for the minerals. That means the chemical composition components available for mineral formation, right? So you have clinopyroxenes in the range of 50%, around 50% of calcium. So those clinopyroxenes you can consider, you can find as diopside and Heidelbergite, right? So if the iron content is greater than 50%, because you see this is the 50% iron, 50% iron and 50% magnesium, right? This is the central part. So along that line, so from these two sides, you have 50. This is the mark, 50 mark, 50 iron and 50 magnesium. Sorry. So what you have is, if the iron component is rich, then it's going to Heidelbergite composition, and if the magnesium component is enriched, then it's called diopside composition. So the calcic pyroxenes or clinopyroxenes, sometimes we refer it as calcic pyroxene. So these pyroxenes you can broadly categorize into two as Heidelbergites or diopsides based on the ratio of calcium and magnesium. Okay, but at the same time, you know, the similar amount of calcium is enriched there, because you see the distance is same along this line. So therefore, the calcium component is almost same, right? It's almost same, only the iron and magnesium changing. So those iron and magnesium are changing under solid state condition. So we call it diffusion control. Diffusion means ionic substances are moving in atomic scale, right? Movement of ionic substances at the atomic scale. Okay, so if it is in other words, we call solid solution. Okay, so that causes this pyroxene variation, compositional variation. So calcium does not change much. It's almost around that range, but it's of course it can be variable in this range, right? In this range, that means about 40 to 50, like, it can be variable. In extreme cases, there are more higher compositions, but in general, calcium component is variable from 40 to 50% in clinopyroxene. That is the main series of clinopyroxene, diopside and Heidelbergite. In addition, there is a specific composition called Ozoid composition. Ozoid. It's little bit less calcic, right? So it goes down mean from here. It goes down mean the calcium component is low, right? So calcium component is low. If iron and magnesium is almost 50 like, right? Around 50. That's why it's coming towards the central part of this triangle here, right? So that composition may be variable like this, okay, along this side, iron rich composition and maybe magnesium rich composition, slightly variable calcium component is there. That particular composition is called Ozoid composition or Ozoid composition. So you can see here, you have iron, magnesium, iron, and calcium, right? These aluminum, silicon, these things are anyway there in pyroxene. Whatever the pyroxene, you have these components. So solid solution changing components are this set. Okay. So additionally, some sodium can also be there, but it's not essential for Ozoid. Sodium can be accommodated, but not necessary. So that composition is mainly calcium, magnesium, iron, silicate. Okay, aluminum silicate, right? Those that is the Ozoid composition. But you know, already any pyroxene, any kind of pyroxene can be represented as calcium, magnesium, iron, aluminum silicate, right? That is possible. But only thing is for Ozoid, slight differences are there in calcium components, and also the optical characteristics are different from diopside to Heidelbergite. The optical characteristics are also different, but in microscope, under the microscope, or under the optical microscope, it's very difficult to distinguish diopside and Heidelbergite. It's not easy, right? Some slight color variations may be there, but you can't recognize whether it is diopside or Heidelbergite under the microscope, right? Because it's a chemical variation only, right? Here you see iron and magnesium enrichments are there alternatively. So that difference cannot be detected by an optical microscope, right? It's very difficult. So for that you have to do some other method. That's what you call EPMA, electron probe microanalysis, where you can understand the chemical composition. Okay, so the thin section itself can be used for that purpose as well. Anyway, that difference is there, but you are not supposed to distinguish diopside or Heidelbergite under the microscope. Okay, and most of the rocks that we use in our lab are mainly high temperature type of rocks. That means we call granulites. You will learn these things soon in the next semester about rocks. So these rocks contain diopside rather than Heidelbergite, right? So our rocks mainly contain diopside if they are clinopyroxenes, and to some extent there are Ozoid also. Ozoid can be distinguished from the using the color variation also. You will learn about these things when you have the practicals. Okay, right. So anyway, you remember there's a miscibility gap. So in other words, a liquid immiscible region, right? Sorry, solid immiscible region. There you can't have a solid solution to exist. Okay. And there is another type of pyroxene which really cannot be categorized as a clinopyroxene, but it's not an orthopyroxene as well, right? That is what you call the pigeonite. Okay, so this pigeonite is a special kind of pyroxene which you can consider in some cases as a clinopyroxene, but it's not really a clinopyroxene. But people, in the literature, some researchers have considered it as a clinopyroxene because it contains a little, comparatively high amount of calcium compared to orthopyroxene, up to this range. Okay, slightly higher, more than 10 weight percentage there. So it can be considered as a clinopyroxene, but it's not real clinopyroxene, because if it is a clinopyroxene, it should come under this region. I mean, it should plot, its chemistry should plot along this region. Okay, but this is a particular, this is very specific pyroxene. But still it is under monoclinic also, therefore it's no harm that you consider it as a clinopyroxene. Okay, so it crystallizes in the monoclinic system, and it's really at high temperature, right? It crystallizes at high temperature is a requirement for pigeonite to crystallize, right? It's at high temperature, it's crystallized. And although it's a clinopyroxene, as I said, there's a miscibility gap between ozoid and pigeonite, right? That means they never mix each other. But ozoid Heidenbergite, ozoid diopside, or diopside Heidenbergite, they can mix each other under solid state condition. That means diffusion can control their chemistry, but ozoid and pigeonite composition cannot be changed under solid solution conditions. That is what you call the miscibility gap. Clear miscibility gap exists. That's why you don't see any kind of pyroxenes in this region. Okay, right. So I said that this pigeonite specifically crystallizes at the high temperature conditions. So obviously that means at lower temperatures, pigeonite is not stable. Okay, so pigeonite is not stable at low temperature. So you can clearly expect that at low temperatures, it should dissociate. It should break down into ozoid and OPX. Why does it change into ozoid and OPX? That is the closest composition. You see here ozoid you have, and here orthopyroxene you have, right? So ozoid and orthopyroxene can be formed out of pigeonite. So that is happening under low temperature. I mean, when the rock subject to low temperature conditions, suddenly from high temperature conditions, this reaction can take place. Okay, so this is a and also again this is a solid state condition reaction. No melt is involved or melting is required. So under solid state condition, diffusion can do this change, right? So it's a specific physical condition change. That's why it happens. Otherwise, this will not mix each other. I mean, there will be no mixing or solid solution or whatever under high temperature conditions. But when the rock changes suddenly from high temperature to low temperature, this type of change can happen. This is we call decompression reactions. We call decompression reactions or cooling reactions sometimes because it's temperature sensitive, right? Rather than pressure, it's temperature sensitive because pigeonite is highly sensitive to the high temperature conditions. So if the temperature changes, its stability breaks down. So that happens. So usually this pigeonite is found mostly in hot volcanic rocks because high temperature conditions are required for that. So very hot magmas, this pigeonite can be found. And also in shallow intrusive igneous rocks. So you will learn about intrusive igneous rocks later on in the next semester because there are different igneous rock types. So you will learn about that separately. Okay. And also they can be found as exolution laminates. So what is exolution laminates? You may have get the opportunity, no, still not, I think. You will have, I mean, probably Dr. Dharmapi may have shown you some images of exolution. That is a very common feature you can find in pyroxenes under the optical microscope, right? So I will show that. So this exolution happens due to this type of reactions, the solid state reactions under diffusion control. So temperature variations most of the time cause these exolutions to happen. So exolution means you have one, suppose you have one mineral, say this is pigeonite. Okay, so if the temperature drops suddenly, right? If the temperature drops suddenly, the whole pigeonite grain will start to change into Ozoid and OPX. This reaction will take place, right? But this does not happen at once. Okay, it happens gradually. So at a place, in a local place where the diffusion can start easily, the ion migration can start easily. It depends on crystal chemistry of the rock and also the crystallography and crystallography mainly chemistry, how the ions are substituted into the structure. So one place it will start, right? So again, another place it might start, another place it can start. Likewise, locally it starts to appear, right? So in a region like here, maybe you have this reaction happen. That means the entire pigeonite grain now converted into a new mineral locally in one place. Probably this may be ozoid. Okay, this may be ozoid, while some other part like here is converted to the other mineral OPX. Okay, OPX, but still the host pigeonite is there. This is the pigeonite, the host pigeonite. So only locally you see this type of variation. So maybe another place you see this type of change. So anyway, if this temperature drop continued for a long period of time, maybe some millions of years, this grain can be even separated into separate two grains. That means a completely ozoid grain plus completely pyroxene grain, orthopyroxene grain. So that means you might see some faint grain edges where the ozoid, where the pigeonite was existing. Right now, no longer pigeonite is there, but instead you have a lot of small ozoid grains and small OPX grains. So this type of reactions can take place in rocks. But remember, this all these things are happening under solid state conditions, right? Nothing in the liquid state. That means there is no melting or anything happening. These are solid state reactions. So this can happen when the temperature changes. So that is what we call the exolution. So these things are showing in rocks as like lamellae. You know lamellae, some tiny films right? Like these, we call it lamellae, right? So since this is a product of exolution means diffusion control change of ionic behavior in response to sudden temperature sudden temperature change. These are called exolution laminates, right? So this is exolution laminae found in minerals. So this happens, see, this is the exolution laminates you see in the rock, in the mineral, right? So this is a kind of a reaction. It takes place under solid state condition where this compositional change can happen. Okay. It's a phase change. We call it a phase change. You will learn about the phase diagrams. This is a phase diagram which might not be understandable to you, but you will learn these things in your next year, right? So you don't want to think much on the phase diagrams right now, but just keep in mind that this is a solid state phase change. Phase change means mineralogical change. Phase means mineral. Okay, right. So I will show you the exolution laminates real images taken from optical microscope. See, these are the exolution laminates. So you can see two colors, bright color and dark color. So this dark color is usually orthopyroxene, and this bright color is clinopyroxene. Okay, so this type of reaction, ozoid OPX, means clinopyroxene and orthopyroxene. Both are produced as a result of this exolution. So I said one zone is OPX and one zone is CPX, like that. That is the exolution laminae. So you can see exolution laminae in this grain and this grain and also this grain. And here also a slight exolution laminae you can see. But remember, these are not exolution laminates, okay? This is not exolution laminate, and this is not exolution laminate. This is something else. You have learned it already. Can anybody tell me what this is? These ones. This feature, this particular feature. Yes. What is that mineral? By appearance, can you tell that? You may have learned already now, I'm sure. What is it? Yes. So if you have gone through your content that was taught to you by Dr. Dharma Priya, no, it's not fractures. I got one answer as fractures. It's not fractures actually. You can see fractures separately, but this is not fractures. So what you see very colorful image now here. So what is this image? There are two modes in the microscope, polarizing microscope. I think you have already learned. One is PPL, and the other one is OP. Sorry, OPL, or sometimes yeah, mainly it's called XPL, right? And otherwise CPL. Sorry, right? CPL or XPL, right? And PPL. So these are the two modes. What are these two modes? Plane polarized light, cross polarized light, right? You know these things. Sometimes it's called X polarized lights, right? PPL and CPL. So this image is what? CPL or PPL, OPL or XPL or PPL? XPL mode, XPL mode or CPL mode, cross polarized mode. So that means that's why you see these some colors. Actually, these are not real colors of the mineral. I think you know it already. These are some produced colors by the polarizer, right? In the microscope, these are not the natural colors of minerals, but we call them interference colors. So interference colors means interference in the sense it's a light wave interferences, right? It's a wave, you know. Light wave is a wave, so it interferes with the polarizers so that it produces some fake colors, right? So these are fake color, but we use these colors to identify minerals also. So what is this feature? This is a Plagioclase feldspar grain. This is a feldspar grain. Okay, so you will learn details about these minerals later on, but I think these images have been shown to you, I suppose, right, by Dr. Dharma Priya. So anyway, these are the features, very typical features shown by feldspar, Plagioclase feldspar. We will learn about feldspars little later under this course also. This is called polysynthetic twinning, right? These are twinning features of, not fractures, twinning. Okay, those are twinning features in crystals, right? So that twinning means some kind of intergrowth. The crystals are showing growths together, right? Like this. So these are twinning. So it's very common in plagioclase, but you see it's a not very bright interference colors, almost two shades of ash like here. So it's a typical interference, typical feature of feldspar. It's not exolution, but you see here there is optical difference here. Very clear color differences are there. See, the colors are different. You see some zones are there. Okay, it looks like a fracture, but it's not really fracture, because fractures we identify under PPL mode, right? Plane polarized mode. In the plane polarized mode, if you see this type of lines, that is definitely fracture, because if you change this mode into PPL, if you have the same view, you will never see these lines under PPL, right? So that means it's not fracture. If it is a fracture, you must see that is that under PPL also, right? But if you suddenly change this into the PPL mode, you will not see these lines. So that means these are not fractures, or even these are not cleavages. Okay, right? So these are optical features. They are crystallographically controlled features, right? So this is the exolution. So you can see here also clear exolution. One dark line, one bright zone, dark line, one bright zone, like that alternatively you can see. Okay, so these are the exolution features, and here also you can see some lines of features and some other colored areas. It is not necessary to have a line like this feature, right? Although you see, but here also you can see some zones, not real lines. Okay, so that doesn't matter. That is also exolution, right? Okay. Right, so this is what happens under solid state conditions. So this is an example for exolution of pigeonite. Like this is not necessarily pigeonite, right? Always exolution does. I mean, if you see exolution, it doesn't mean that it always associated with pigeonite. Other pyroxenes are also there, right? Diopside, Heidelbergite. Like those client pyroxenes are also there. So anyway, alternatively, OPX and CPX lamellae can be found in a rock, in a mineral, right? In a big pyroxene grain. Usually, this is shown very clearly by big grains, right? So this is anyway due to physical parameter change. Physical parameter means pressure and temperature, right? Pressure varies with the depth and temperature varies also with the depth, and due to a change of temperature when you go deeper and deeper in the Earth's interior, these physical parameters can change. Okay, right. So that is the exolution features in pyroxenes, and if I show you some of these common common pyroxene species, you have diopside here, right? So the natural occurrence of a diopside is here. It's a very beautiful greenish variety, and you have the augite also, right? Augite also here. It's a more dark, like more brown, blackish to brownish color, right? It's not like the greenish appearance in diopside. Heidelbergite is also greenish, so that's why I told you that it's not easy for you to differentiate the diopside and Heidelbergite easily. But being magnesium rich, I mean, even diopside, it's going this way. That means it's magnesium rich. So when you have magnesium rich varieties, there is tendency for appearance of green color, right? But it's not a rule. But most of the cases it happens. But when it mixes with iron, so that means it's going to Heidelbergite series. It can have some iron in enrichment, so this color changes, right? It's coming more brownish like appearance, but again it's not a rule, because atomic arrangement and atomic replacements with trace elements also can change the crystal color. So therefore it's very hard for us to rely on only on the major elements, right? The major elements means is magnesium, iron, calcium like elements, right? Which are abundantly found in the structure, right? Even a tiny amount of titanium, if present in the structure, they can replace either magnesium or iron, ferrous. They can vastly change the color of the mineral, right? For gem varieties, this is very important, right? To get the beauty. Okay, right. So here you have the enstatite variety, but you see enstatite is also magnesium rich variety, but it's an autopyroxene, but it's not greenish. That's the thing. See, it's not greenish, it's more brownish color, right? Actually, Heidelbergite, it goes towards more yellow, honey brown, like it's not brown really, a yellowish color, right? Not this brown color. Okay, right. Anyway, this is enstatite, so you see it's more brownish, but ferrocylite is very dark. It goes like this color, like it's dark, although there is no image here. There's a special pyroxene, we call it hypersthene. Sorry, This should be hypersthene. Okay, and hypersthene. Okay, hypersthene. You may have heard of this hypersthene because in our rocks there are many occurrences of hypersthene, especially in the rock type called charnocite. You may have heard of this rock type. You will learn about these things in the next semester. Charnocite essentially contains hypersthene, right? So the hypersthene composition plots here, right? Exactly around 50, right? It's not really 50, but maybe variable in this range. Okay, very close to 50-50, iron and magnesium both, right? That's hypersthene composition, and it's a high temperature mineral. Therefore, we see a lot of hypersthenes in our rocks. Our rocks are generated under high temperature conditions. So we will learn details later on. So in the rock, so this is a granitic or metamorphosed granitic rock, one of the rock types that you are going to learn in the next semester. There you see these brownish areas. These brownish areas are the typical hypersthene appearances. So these are the typical orthopyroxenes. So you basically you understand orthopyroxenes are not very colorful like clinopyroxenes, but there are colorful orthopyroxenes as well if they are very fresh, right? Some mainly yellowish to brownish colors are there in orthopyroxene, but clinopyroxenes are mainly greenish varieties, greenish to very light or pale yellow colors like. Okay, so these are the common types of pyroxenes that we have in many types of rocks. So yeah, please put your number and your name to mark the attendance. That is important. So please type it in the chat box. Okay, right. So this is regarding the normal pyroxene series. But I think we reminded last time one special type of pyroxene is also there. That is what we call the sodic pyroxenes, right? Sodic pyroxenes means you see sodium enriched pyroxenes. So normal triangle, the pyroxene triangle, what you have elements, magnesium, iron, and calcium, right? But there is no place for the sodium to accompany there, right? So that composition comes actually, I mean, the sodium, when you want to accompany sodium, you have to create a triangle like this, because you have sodium, not only sodium, and iron is also there, ferric iron, but not ferrous. Previously we had ferrous. So ferrous is here. You have ferrous here, you have magnesium here, and you have calcium here. So that previous triangle, this triangle, the typical pyroxene triangle is plotting on top of the new triangle where we have accommodated sodium, because sodium is there in very large amounts. So that means all the three iron, that means ferrous, right? This ferrous, magnesium, and calcium, all divalent atoms or divalent ions are found in very little amount, less than 20%. So you see, this is the 20% region. So in this 20% region, you have that entire triangle which we represented previously, right? So these pyroxenes are more high temperature varieties, because the previous pyroxenes we call calcic pyroxenes, orthopyroxenes, and clinopyroxenes, which are having typical pyroxene compositions, right? Diopside, Heidelbergite, phaelite, ferrocylite, like those compositions are having they are preferring high temperature conditions, so we call them high temperature pyroxenes. So when it comes to high pressure regions, sodium comes into the structure in very large quantities. So that makes all these previous high temperature pyroxenes to be having composition very little, less than 20%. All the rest is sodium, right? Monovalent cation. In addition, you can have ferric also, trivalent cation as well. So Under high pressure conditions, so high pressure conditions, these pyroxene compositions entirely change, right? So they are getting more sodium into the structure and more ferric into the structure rather than divalent cations. Okay, so these are high temperature kind of pyroxenes. Okay, but from there downwards, you have high pressure type of pyroxenes. But the requirement is you need to have a increased pressure condition. Okay, right. So the variety is mainly the end member jadeite, right? Jadeite is considered as a gem also, right? So you have jadeite here, and when the sodium plus ferric is also there, then the composition is called azurine. It's azurine. Okay, so you have jadeite, azurine, and when it goes to having a little more ferrous, magnesium, and calcium composition, right? Because this entire composition is represented by this end. Okay, so that means when you go this way, not only calcium but also ferrous and magnesium also increase. All the three components will be increasing. That pyroxene, the newly forming pyroxenes, are either omphacite or azurine ozoid. Omphacite or azurine ozoid, depending on whether it's a sodium rich site or ferric rich site. If it goes to ferric rich site, then it comes as azurine ozoid, entire composition. So there's a huge compositional variation in this pyroxene, in this sodic pyroxene series. So these are called sodic pyroxenes. Okay, so they are formed under high pressure conditions. So high pressure conditions means the places like subduction zones. So you know, oceanic crust subducts beneath the continental crust due to the density variations. Oceanic crust is heavy compared to the continental crust, so that subducts beneath the continental crust where higher pressure conditions are created. So these higher pressure conditions will cause sodic pyroxenes to form rather than calcic pyroxenes. So some reactions are also there. So these are also taking place under solid state conditions. There is a mineral called nepheline, and it reacts with albite. Albite is a group of mineral under feldspars. Okay, sodium rich feldspars. We will learn about that later on in this lecture series. Nepheline and albite forms jadeite, right? It's a reaction when the pressure increases, right? Increase of pressure is a requirement for this reaction to continue. And also there is possibility to form a jadeite directly from albite. Okay, directly from albite. In that case, jadeite plus quartz is produced. Not only jadeite plus quartz is also produced. Okay, still you need pressure conditions, higher pressure conditions, but different pressure regions. In different pressure regions, these two reactions are taking place, right? Anyway, jadeite is the main product. So likewise, there are many reactions to take place to form these each and every sodic pyroxenes also, right? So at the moment you don't need much to concentrate on the reactions, because under petrology you will concentrate on reactions, right? So as I mentioned, these contains sodium and ferric, right? So sodium is monovalent and ferric is trivalent. They are having two valent cations substituting at the same time, because into the pyroxene structure, sodium enters, that means monovalent cation. At the same time, ferric is also entered to the same structure, pyroxene structure. So ferric is 3 plus, that means trivalent. So this monovalent and trivalent substitution, monovalent and trivalent ionic substitution takes place together at the same time, right? So at the same time means they are formed they are replacing synchronously. So that is called coupled substitution. That is called coupled substitution. That means there are two substitutions are taking place at once. So that is coupled substitution, because the valency is different in these substituting materials. Okay, monovalent and trivalent cations are substituted. So therefore, we call it coupled substitution is there in sodic pyroxenes. So under high pressure conditions, this coupled substitution is a very common feature. Okay, right. So do we have any questions regarding this content? So if you have any question, please let me know. No question regarding the content that I have delivered? Okay, so I hope everything is clear. No question? Right. So we will go. We will continue then. Okay. Just a minute. Okay. Right. So we will continue then. One more important feature that I have to tell you, that is the cleavage, right? So cleavage, as I mentioned, cleavage you should be able to see either in the hand specimen or in the thin section or the optical microscope image, right? So in pyroxenes, you can see here very characteristic feature, right? Can you see this edge clearly here? So this edge is almost like 90 degree, isn't it? See, this angle is almost like 90 degree, right? It's not exactly 90, but it's very close to 90 degree. So that means pyroxenes tend to have cleavages, two sets of cleavages, which are cross-cutting closely at 90 degrees. Okay, so here also you have a similar type of a cleavage, right? Along the cleavages, the mineral can easily break. That is the cleavage, the definition of cleavage, right? So you have cleavage here. Okay, you have cleavage here. So it's clear that you have cleavage produced there. Okay, so this cleavage is very common feature found in pyroxenes. This is a common feature found in pyroxenes in this case. Okay, so any questions, please let me know if you have any questions. Okay, right. So this is a very common feature, but you don't need to draw, do anything with these diagrams, because these are very complicated diagrams, and you don't need to focus much on this these crystallographic sites, we call them crystallographic sites. Okay, right. So anyway, 90-degree cleavage is there, so that's why you see this pyroxene is breaking into 90 degrees, right? So these two sets of cleavages are showing in pyroxene structure. Okay, so this is the image under the optical microscope. You can see they are having a very close 90 degree or 87 actually. This is really speaking, it's 87. Okay, so this edge also should have 90 degree. Okay, that's why it's broken. So these are broken, but ideally it must have a 90 degree angle here like this. Okay, right. So you can see here also 90 degree cleavage. So these are the cleavages that you can find in in pyroxene, any pyroxene, clino or orthopyroxenes. Okay, it's clearly you can see these two sets of cleavages. Okay, right. This is a characteristic feature that you can use to identify pyroxenes in from other minerals, because other minerals don't have this specific two sets of cleavages crossing at 90 degrees or perpendicular cleavages. Okay, any question? So do you have any question? Okay, so if no question, so I have to attend a meeting now on, so therefore I will stop the lecture here. So we will continue it at the next time. So I want to have fix a time for the lecture. Maybe I don't know. Maybe on Sunday, probably, if you have time. But please let me know a suitable time, or otherwise we can fix it next week. But the next week, I think you have some tentative calendar was prepared by the faculty. But I think your academic session was postponed until the November 1st, isn't it? If we have time, we can continue on the next Friday as well to finish it up. Otherwise, I have to take a extra time, right? So you can suggest me a suitable time available with you. Okay. So otherwise, I will fix a class and let you know in advance, so that you can let me know whether any other lectures there or not overlapping that time slot. Okay. So any other question? Anything else? If not, I will stop here. You can email me regarding the specific requirement on this that the discussion is also necessary, so we can fix a time for that also. Okay, so I'm stopping here now. Have a good day.